Here's a problem that will introduce the concept that's in the title of this section, which is rates of change. And it's we're using the example of a driver going from Quebec City to Montreal, and he's going to travel 250 kilometers, and the duration of his trip is 2 hours and 15 minutes, or 2.25 hours. Now, there's nothing that says here that he's driving at a constant speed, or that he didn't stop for a bathroom break or maybe for lunch. So one way to illustrate like what his trip could be like is to create a graph where the x-axis is actually the t-axis is for time, so time in hours, and the y-axis is actually the d-axis, where d represents distance traveled. So initially, he's in Quebec City, right? So when the distance travel is 0, he's in Quebec City, and when he's going to arrive to his destination, he's going to be right here, and this is Montreal. Okay, so we know that when t0 is in Quebec City, when t is 2.25, 2.25 is roughly here, E is in Montreal, so right there. Okay, so let's indicate those points. This is 0, 0. This is 2.25, 250. And as time goes by, he could, typically will increase the distance traveled, but nothing prevents him. After an hour, maybe he stops for. This is him stopping. You see his the value of d here is constant, so he's not moving. Time goes by, but the d doesn't change, so it's flat. So maybe he stops for Tim Horton for a muffin and a coffee, and then he hits the road again, and then eventually gets to Montreal. Okay, so anything's possible here. Obviously, there are other curves that you could actually travel at a constant speed, which would look like this. Or you could, start really slowly, like this, and then go real fast in the end. Okay, so all these trajectories are possible. But one thing that's pretty clear is that if he's going at constant speed, is the rate at which distance is going to increase is going to remain constant. Okay, so we're going to have a constant slope. So this is if he drives at a constant speed. Okay. Now how do we calculate his speed then? Okay. Maybe I'll try. I'll write in green because this is related to the curve in green. So his speed for the green curve, okay, is very easy to calculate. So it's constant. So it's just you calculate distance traveled and you divide by time. So here he's traveled 250 kilometers, traveling during 2.25 hours. You calculate this, you get 111.1 repeated kilometers per hour. So to calculate this, we basically looked at this triangle here, formed by the trajectory and the two legs of the triangle, and we basically are looking at change of y over change in x, or actually maybe here it's a change in d over a change in t. So we've basically calculated delta d over delta t, and that's why we're calculating a slope here. Okay, so this is basically the slope of the dotted line. Now this speed actually corresponds also, if we look at the red trajectory, to the average speed of the driver. So actually, no matter how he gets from Quebec to City to Montreal, if he drives 250 kilometers during 2.25 hours, his average speed is going to be the same no matter how he gets there. So we're going to write this. This is the average speed of the driver. We can also say, more generally, it's the average rate of change of the distance over time. So an average, how distance changes over time. So it's changing essentially at a rate of 111.1 repeated kilometers every hour. That's how it's changing in the average. Okay. So we're gonna abbreviate average rate of change with ARC. And ARC is usually over a time interval or over some interval. So we're gonna have an interval AB here, something like that. Okay, in our case, A starts at is the initial time 0, and it ends at 2.25 hours. So I will show you another example. This time with, I'm going to give you a function. We're going to sketch the graph of y equals f of x. So f of x is the name of the function, and it's x squared plus 1. So x squared plus 1, x squared looks like this. Okay, and then to every y coordinate, we increase the value by 1, right? Y increases, right? If this is y equals x squared, for example, this could be 1, 1. If I'm looking at now y equals x squared plus 1, for the same x, the y would now be 1 more, 2. So what this does to the curve is that it shifts it up by 1 unit like this. So we're going to graph this curve here. So, something like that. Okay. And let's look at two values of x. So this is x, this is y. We're going to look at two values of x. I'm going to call them x1 and y1. And x2, sorry. And just to maybe have some numbers in mind, let's say the first one is 2, the second one is 4. For each value of x, there's a corresponding value of y on the curve. I'm going to call that y1. And this one, I will call it y2. And what we'd like to know is the average. So what is the average rate of change of the function f on the interval x1, x2, which is in this case 2, 4. Okay, and just like for the speed problem before, like the average rate of change is just going to be the slope of the line connecting the 2 points. We call that line the secant line. So this is called a secant line. So the so it is the slope of the secant line passing through x1, y1, and x2, y2. So we just need to calculate a slope here. So ARC, average rate of change over the interval 2, 4. Okay, or maybe actually let's use x1, y1 first, because I'll use that to get a general formula. Okay, how do we calculate this? Well, we do delta y over delta x. So it's going to be y2 minus y1 over x2 minus x1. Now y2, what are my 2 points here? Y2 is, well, this is x1, y1, but y1 is actually the function value at x2. Y2 is the function value at x2, and y1 is the function value at x1. So instead of y1, I'll write f of x1 here. And this is x, oh, I messed it up. This is x2 f of x2, sorry. x2 f of x2, like that. And this is x1 f of x1. So here, f of x2 minus f of x1 over x2 minus x1. So that's our general formula. So in our specific case here, we've got x1 and x2 are 2, 4. So it's going to be f of 4, sorry, over minus f of 2 over 4 minus 2. So f of 4 is, you square it and you, remember the formula for f of x is x squared plus 1. So f of 4 is going to be 16 plus 1, so 17. F of 2 will be 2 squared plus 1, so 5. And divided by 4 minus 2, so that ends up being 12 over 2, so it's 6. Okay. And if we ever need to have units here, it's going to be units of y over the units of x because of this. Okay. So when you subtract y's, you're not changing the units. Let's say y are in kilometers, right? It's kilometers minus kilometers, so it's kilometers above. X2, let's say it's in hours. Hours minus hours is hours. So overall, you get kilometers over hours. So it's very easy to figure out the units of your average rate of change. So 2 things to remember from all of this: this formula for the average rate of change over an interval, that's important. And the fact that it's the slope of a secant line. That's also important because it gives you a geometrical understanding of what it is.